JAR OPS 1 requires that if the obstacle cannot be cleared by a vertical margin of 50 feet, then the aeroplane must be able to demonstrate a minimum horizontal obstacle clearance. This horizontal clearance is calculated by using a simple formula. For a wingspan of 60 meters or more, the horizontal clearance is 90 meters plus 0.125 times d. For a wingspan of less than 60 meters, the formula is 60 meters plus half the aeroplane wingspan plus 0.125 times d. d is the horizontal distance from the obstacle to the end of the takeoff distance available, or the end of the takeoff distance if a turn is scheduled before the end of the takeoff distance available. When complying with the horizontal clearance regulations, for those cases where the intended flight path does not require track changes of more than 15 degrees, an operator need not consider those obstacles which have a lateral distance greater than 300 meters, provided that the flight is conducted under conditions allowing visual course guidance navigation, or if navigational aids are available, enabling the pilot to maintain the intended flight path with the same accuracy. For flights under all other conditions, horizontal clearance is 600 meters. For those cases where the intended flight path requires track changes of more than 15 degrees, an operator need not consider those obstacles which have a lateral distance greater than 600 meters for flights under conditions allowing visual course guidance navigation, or 900 meters for flights under all other conditions. Expressed more simply, these regulations are telling an operator that he needs to use the obstacle clearance formula only if the obstacle is within the lateral distances shown in the table. Let's work through an example to illustrate how the horizontal clearance requirements work in practice. The specimen aeroplane used in CAP 698 is the Piper Seneca, whose wingspan is approximately 12 meters. Therefore, in the formula, half the wingspan is 6 meters. D represented the distance from the end of the takeoff distance required to the obstacle. And in our example from earlier, we used 9,000 feet as being the distance to the obstacle, which is 2,744 meters. The formula gives us a horizontal obstacle clearance of 409 meters. Although the horizontal obstacle clearance formula tells us that the obstacle must be cleared by 409 meters, whether or not we use this figure depends on the margins and conditions shown by the table. Using our earlier example, the aeroplane is in the cloud and therefore the pilot is unable to navigate visually. Therefore, the part of the table which concerns us here is the IMC row, which you see highlighted. Let's assume the aeroplane makes track changes of less than 15 degrees. This would mean that all obstacles within 600 meters of the aeroplane have to be considered. If an obstacle were to be within 600 meters from the aeroplane, that obstacle would have to be cleared by a horizontal margin of 409 meters. If the obstacle was further than 600 meters from the aeroplane, it would not be necessary to carry out the horizontal clearance calculation. In summary, then, the rules state that the aeroplane must clear all obstacles by 50 feet vertically. If the aeroplane is unable to do this, then it must clear any obstacle within the obstacle clearance area by a horizontal distance as calculated by using the horizontal clearance formula. We mentioned earlier in the lesson that there were two main requirements for multi-engine Class B aeroplanes in the climb. The first requirement concerned obstacle clearance, which we have just covered. The second part of the regulation deals with minimum acceptable climb gradients after takeoff. You may remember from an earlier lesson that the minimum climb gradients specified by the authorities are air gradients and therefore independent of wind. JAR OPS 1 states that with all engine operating, the steady gradient of climb after takeoff must be at least 4%. The following special conditions have to be taken into account when demonstrating this gradient during certification. With one engine inoperative, the steady gradient of climb from an altitude of 400 feet above the takeoff surface must be measurably positive, with these assumed conditions. From an altitude of 1500 feet above the takeoff surface, the steady gradient of climb must be not less than 0.75%, with these conditions assumed. The aim of these minimum climb gradients is to ensure that the aeroplane is operated within an appropriate safety margin. The maximum mass that will allow the aeroplane to attain the minimum gradients is called the climb limit mass. Exceeding this mass will mean that the aeroplane will not be able to attain these minimum regulatory gradients. Graphs which enable the pilot to calculate the gradient of climb are provided in most pilot operating manuals or aeroplane flight manuals. An example of this type of graph can be found in CAP 698 on page 13 of section 3. As with all graphs, before you use it, ensure you are familiar with the associated conditions applying to that graph. In this example graph, the assumed conditions are that the throttles are set at takeoff power, mixture is rich, and that flaps and gear are up. The climb speed for the graph is taken to be an indicated airspeed of 92 knots for all masses. We mentioned at the beginning of the lesson that obstacle clearance requirements and climb gradient requirements are published in JAR Ops 1, and that abbreviated versions of these requirements can be found in CAP 698. We have already discussed these requirements, but we will mention them again as we read through CAP 698. These requirements are on page 9 of section 3 in CAP 698. At the top of the page, the first paragraph contains the definition that the takeoff climb extends from 50 feet above the surface at the end of the takeoff distance required to 1500 feet above the same surface. The paragraph also mentions that takeoff power is applied for only 5 minutes, after which time maximum continuous power must be set. The next paragraph states that if the visual reference to the obstacle is lost, in other words if the pilot enters cloud, it must be assumed that the critical engine will fail. The paragraph also specifies that all obstacles must be cleared by a vertical interval of 50 feet. The next sentence states that turns are not permitted before the end of the takeoff distance required, and thereafter must not exceed 15 degrees angle of bank. Paragraph 3.1.1 gives the formula for calculating the horizontal clearance that must be maintained if the aeroplane is unable to clear the obstacle by 50 feet vertically. However, only those obstacles within a certain lateral distance from the aeroplane, as shown by the table, need to be cleared horizontally by the distances calculated from the formula. Lastly, in paragraph 3.2, we find the climb gradient requirements for all engines operating, and for one engine inoperative. Even though the CAP 698 provides you with a lot of information, it does notably omit two very important requirements when considering obstacle clearance. The first piece of missing information is that you must factor the all-engine gradient by 0.77. The second is to adjust the gradient for the effective wind using the 50% headwind and 150% tailwind rules. Therefore, ensure you commit these regulations to memory. There are some example calculations in CAP 698 for you to work through and practice. For example, on page 12 of section 3, there is an example on how to calculate the horizontal distance travelled from the end of takeoff to 1500 feet. On page 14 of section 3 is one other example. This example shows you how to calculate the aeroplane's vertical clearance of a given obstacle. The examples mentioned and the ones in the question bank are all important. They help you to practice the theory you have learnt and familiarise you with the types of questions that you may encounter in the ATPL exam itself. You must be aware of what the CAP manual can and can't provide for you. Familiarity with CAP 698 will give you a better sense of what you do not need to commit to memory for the exam. This completes the lesson on Class B multi-engine climb requirements. From this lesson, you should have learnt what the climb requirements are and also how to calculate your aeroplane's climb performance in order that you comply with the regulations.